Welcome to the second part of lecture 4. In this lecture, we'll be talking about an important principle which will basically help us in combining observer and controller design for one system, which is called the separation principle. Now consider that you have a controllable and an observable system which is given by x dot is equal to ax plus bu, y is equal to cx. Assume that you have designed a state feedback law given by u is equal to minus kx for the system. In effect, arbitrarily placed the poles of the system according to your choice, and you have also designed an observer which is given by x hat dot is equal to ax hat plus bu plus m y minus y hat. And this observer also, say for example, has an output given by cx hat because you're using this for observer design. So you have, for this controller and controllable and observable system, you have designed a controller and you have designed an observer. Now the question is, you are providing a state feedback law based on the observer state x cap, not on the basis of the original full state, that is x. So basically your controller is now u is equal to minus kx cap instead of u is equal to minus kx. So what do the overall dynamics of the plant become, and how does the plant look like? So if you want to sketch this, it will be something like this. You have a plant which responds to the input. The dynamics are x dot is equal to ax plus bu. You have a C matrix, get y. And here you have an observer which is x hat dot is equal to ax hat plus bu plus m y minus cx hat. Please remember that your y hat is cx hat, and you're taking this y input from here for the observer because this is one of the inputs that is going into the observer, and you're taking this u input here from the observer because this is another thing that is going into the observer, and based on this you are calculating x hat, and this x hat you are multiplying it with minus k, and this is actually your controller here. So this part is your controller, which is observer based controller, and this part is your observer. So this happens when you're actually trying to implement a control law based on the observer that you have designed. Now we have seen on the last two turns that when you design a controller, you are able to have control over the eigenvalues of a minus bk, which in effect gives you control over the behavior of the plant. And when you design the observer, you have control over the eigenvalues of a minus mc, which gives you control over the aerodynamics of the observer. Now the question is, you design the controller separately and you design the observer separately, and you proved these two things. But now you have combined the two. So the question that automatically arises is, do you still have control over the eigenvalues of a minus bk and the eigenvalues of a minus mc? That is, can you still arbitrarily decide what should be the dynamics of the plant, and also arbitrarily decide and fully control the aerodynamics of the observer? So this is what we're going to see, and we'll be able to see that you have control over the eigenvalues of a minus bk, and you also have control over a minus mc, eigenvalues of A minus MC, and you're able to basically separately design the controller and the observer and then implement the two together, and this is called the separation principle. So now let us look at the equations. So you said that your plant, we said that a plant was x dot is equal to ax plus bu, y is equal to cx, and the observer is x hat dot is equal to ax hat plus bu plus m y minus cx hat, and this is the observer, and based on this observer you're applying the control law u is equal to minus kx hat. So how do the equations change? Now let us try and put this equation back up here. So you get x dot is equal to ax minus bkx hat, and let us manipulate this a bit. So let us add a minus bk, add bkx and subtract bkx from this. So when you add and subtract bkx, you take the minus bkx in here and the plus bkx in here. So you'll get a minus bkx plus bkx minus x hat, and this you can write as a minus bkx plus bk. You already know that this is x tilde. So this is one equation, and the other equation that you already have for x tilde is x tilde dot is equal to a minus mc x tilde. So these two equations now describe the dynamics of a 2n dimensional system, because you have added n dimensions. You have added one observer which is of n dimensions, so the overall system is 2n dimensional. This includes these are the dynamics of the 2n dimensional system, which you have drawn above here. This one. This is the dynamics of the 2n dimensional system. And this 2n dimensional system includes the plant, it includes the observer, and includes the controller. Now if you write this separately, you can write x tilde dot is equal to a minus bk 0 a minus mc x tilde. Now this equation, matrix equation, has a characteristic equation given by the determinant of si minus a minus bk into the determinant of si minus a minus mc equal to 0. This is because of the 0 term here. So the determinant of this overall system is equal to the determinant of this si minus this into the determinant of si minus this. This is a matrix property for matrices which have zeros, which have a zero matrix here. So the overall determinant of the system is this, which means that the eigenvalues of the combined system consist of the union of controller and observer poles, or eigenvalues, controller and observer eigenvalues. because when you say that the product of these two determinants is 0, that means individually Si minus A minus Bk, this determinant is 0, and Si minus A minus Mc, this determinant is 0, which means that the design of the control law and the observer law can be done separately. So the design of the controller and the observer can be done separately. So when you design the controller separately, you ensure that Si minus A minus Bk is 0 at those values of S for which you want it to be 0. And when you design the controller, you ensure that Si minus A minus Mc is 0 for those particular values of S for which you want it to be 0. And in effect, you're ensuring that your overall determinant for the overall system is 0 for those values of S. So when you implement observer-based control, you are able to actually do it by separately designing the observer and the controller for the system. Observer and the controller for the system. Now, this observer-based controller, what is the equation for it? Now you see, what does it respond to? It responds to the input y and the output is u. The output is u, right? So if you write it like this, x hat dot is equal to a minus mc x hat plus bu plus my. This is by taking the okay, let me write it again. So your actual equation for the observer, if you see from what you have written, is x hat dot is equal to ax hat plus bu plus m y minus cx hat. So I take this term in, so I get x hat dot is equal to a minus mc x hat plus bu plus my, and I then substitute this u with, because your u is minus kx hat, so again I get x hat dot is equal to a minus mc minus bk x hat plus my. So this is your observer based controller, or you can say your compensator. This is your compensator dynamics, and the output of the compensator is u is equal to minus kx hat. The input of the compensator is y, input to the compensator is y, and the output from the compensator is u. And this is also evident from the diagram that we have drawn here, where it actually takes the input from the system y and then gives this input back, gives an output which is u to the plant in order to control it. You can also find the transfer function of the compensator from these two equations. So the transfer function, the output now is us and the input is ys. I'm taking this minus sign here because there is a minus sign here, and I don't want a minus sign in the transfer function. So this is the transfer function of the compensator which is the observer based controller is equal to, now the transfer function would be C, which is in this case K, Si minus A inverse, Si minus A minus MC minus BK inverse, C into Si minus A into B, which in this case is M. So this is the transfer function of the compensator. So in effect, to conclude this lecture, what we have seen is that you can design an observer-based controller by separately placing the poles of the controller according to your requirement. This is determined by what is the behavior of the plant that you want, and separately placing the poles of your observer according to your requirement, depending upon what kind of observer aerodynamics you want. And consequently, the compensator that you get would have this state space representation. Y would be the input to the compensator, U would be the output from the compensator, which is the control law, and the transfer function of the compensator can be written like this. In order to fully understand this topic, I would recommend that you see the solved example 7.7 from the book of M. Gopal. Thank you very much.